All right, let's dive into something really cool today. We're looking at a fascinating patent that sketches out a totally new way of thinking about digital security. It's called combinatorial security, and honestly, it might just be a total game changer for how we send private messages.
I mean, that's the question, right? It's the one that keeps the entire cybersecurity world spinning. Because it seems like every time someone builds a new, unbreakable system, there's someone else, somewhere out there, already figuring out how to crack it.
You know, we're all caught in the middle of this constant digital security arms race. You've got apps like Signal, Telegram, and WhatsApp building these incredibly complex layers of encryption, but the hackers, they're just relentless. The patent actually notes that they are remarkably patient. They'll spend months, even years, just to find one tiny crack, and once they're in, well, that's it. All that private message traffic can become an open book. And this quote from the source material just hits the nail on the head. It's a never-ending cycle of escalation. Even the absolute best systems out there, like Signals, which is brilliant, it rotates encryption keys for every single message. They're still playing the same basic game. They're trying to build a stronger and stronger lock.
And see, that's the core problem. It doesn't matter how tough your encryption is. At the end of the day, you're still sending a complete message from point A to point B. It exists as one single package of data that someone can grab. It's a target. And if the lock on that target can be picked, the game is over.
So this is where it gets really interesting. This patent proposes a totally different strategy. Instead of putting all the effort into building an unbreakable lock, what if we just made the message impossible to find in the first place? The whole idea is about hiding, not just locking. It all starts by basically shattering the message into tiny little pieces called shards. And these aren't neat, uniform chunks of data. For every single message, the system decides on the fly how many shards to make and exactly how big each one should be. The pattern is completely, totally unpredictable. So, where do all these little pieces go? Well, they get scattered across a ton of different servers, which the patent perfectly calls haystacks. And on each of those servers, the system creates this crazy maze of random subdirectories and then hides the shards deep inside them. It is literally hiding a needle in a digital haystack that's constantly changing.
So here's how that whole process looks. First, your message gets turned into just a long, random string of letters and numbers. Then, that string gets shattered into all those variable-sized shards. Now here's the really critical part. Each tiny little shard gets its own unique encryption algorithm, not just a different key, a whole different way of locking it down. Finally, all those pieces are flung across the globe and hidden in those digital haystacks.
Okay, so that raises a pretty big question, right? If your message is in a million pieces scattered all over the world and never actually gets sent, how in the world does your friend ever read it? Well, this is where the real genius of the whole thing kicks in.
I'm going to say that again because this is a whole point. The message itself is never sent from you to the receiver. The little pieces just stay out there, scattered in the cloud.
So instead of the message, what the recipient gets is a tiny notification. The inventor calls it a right to view. And really, the best way to think of it isn't as a key, but as an incredibly complex, encrypted treasure map.
And this map has everything. It's got the exact server and subdirectory for every single shard. It has the specific mathematical formula needed to unlock each one of them. It has the precise order to stitch them all back together, and it has the final key to turn that reassembled mess of characters back into your original message. And as if that weren't enough, the map itself is locked down. It's encrypted with a set of keys that are generated from scratch for every single message. It's like the map is written in a secret language that's invented for just this one trip and then thrown away forever. So how does a system like this hold up against the ultimate threat that's looming on the horizon, quantum computers? We're talking about machines that, in theory, could have enough power to shatter today's strongest encryption in the blink of an eye. This slide just lays it out perfectly. Standard encryption is basically a very, very strong door. A quantum computer is like a battering ram that can smash through any door you put in front of it. But combinatorial security, it isn't a door at all. It's a million grains of sand scattered across an entire continent. The problem for the attacker is no longer about breaking the lock. It's about finding all the right pieces of sand. The patent has this beautiful line. The defense of this system isn't really based on a math problem that can be solved with enough computing power. No, its defense is based on time. It introduces all these little tasks that physically take time to do, like searching through server directories. So just think about it.
Even an attacker armed with a quantum computer has to deal with this logistical nightmare. First, they have to intercept the exact right map. Then they have to break its one-time use encryption. Then they have to digitally race around the entire globe to find every single shard, navigate all the random directories, decrypt each piece with its own special algorithm, put them all together in the right order, and they have to do all of that before the real recipient reads the message and the whole thing gets permanently deleted.
And that is the absolute key takeaway here. You're turning a math problem into a logistics problem. And unlimited computing power doesn't solve a logistics problem. A quantum computer can't make data travel faster than the speed of light. It can't search thousands of servers all around the world instantly. It's a completely different kind of fight, one that's designed to simply run out the clock. Which, it leaves us with this really provocative thought. Maybe we've been focusing on the wrong thing this whole time. Maybe the future of keeping our conversations truly private doesn't lie in building stronger and stronger locks, but in creating much, much better hiding places.